Hello, it's time to get into Module 11, which deals with what is called simple linear regression. You might recall earlier in the course, I believe it was back in Module 3, that we looked at the correlation coefficient between two variables, x and y. We're going to do something similar now, yet different. We still are interested in the relationship between two variables, x and y, but we want to fit a line through the data, which we will call the simple regression line. More specifically, we specifically hypothesize that the variable y is a function of x, where y is going to be called the dependent variable and x is the independent variable. Different books give these variables different names. Y is also sometimes called the response variable or the variable that's being predicted. X is sometimes called the explanatory variable or predictor variable. You might recall when we did the correlation coefficient, it didn't matter which variable we called x and which one we called y, but it will be important here in simple regression. The dependent variable is the y variable, the independent variable, the x variable. Just to give some illustrations, which one would we call x and which one would we call y? Suppose an economist is interested in the relationship between consumer spending and family income. It probably seems logical to argue that how much people spend is a function of their income. So consumer spending would become our dependent variable and family income our independent variable. A labor economist believes there's a relationship between years of job experience and wages. In this case, wages would likely be our dependent variable, and we would likely argue that wages depend on years of job experience. More years of job experience might lead to higher wages. Joe's hot dog stand believes there's a relationship between the number of cases of hot dogs that he sells on weekends and the number of radio ads he ran during the preceding week. In this case, the number of cases of hot dogs would be our dependent variable, or the variable that we're trying to predict. And the independent variable, what we're using to predict our y variable, would be the number of radio ads. Perhaps more radio ads leads to a greater number of cases of hot dogs. The reason we're calling this simple regression is that in simple regression we have only one independent variable. In multiple regression, which you will not get to in a single course in statistics, but in multiple regression you'll have two or more independent variables. Now, we're going to kind of set this up the way we've done throughout the course. Way back at the very beginning of the course, we've talked about how there's a population that we're interested in, but we don't have all data in the population, and we're going to have to just use a sample of data. So we're going to do something similar here. Again, it's not so important to understand the theoretical basis of the model. We're going to be interested in how to calculate a regression line and how to do various estimates from the regression line. But we start with the idea of a population model. I put an equation out here, y equal beta 0 plus beta 1x plus epsilon. That last term is the Greek letter epsilon. You might recognize the first part of this equation. Y equal beta 0 plus beta 1x is just the equation of a straight line with an intercept term of beta 0 and a slope term of beta 1. Epsilon is called the random error term. The way I usually think of it is you're either on this line or you're epsilon distance away from the line. Let's kind of look at an illustration. Imagine we had all data in the population between y and x, and we're going to illustrate a population regression line. Here we have an upward sloping relationship, which would mean that the slope term is positive. So we have a positive linear relationship. Some of these points might be on the line. Many of them will be what we call epsilon distance off of the line. Epsilon is basically the distance of a point to the line. Here we have a negative linear relationship, a downward sloping relationship. And finally, we could have no apparent linear relationship. There could be some kind of a curved relationship in there, but there's no obvious linear relationship. If we take our population model, a couple of ways that we can do this. We could take expected values on both sides, and we will get the equation e of y equals beta 0 plus beta 1x. Another way of understanding this is, let's go back to our population model for a moment. Given a value of x, there's an entire distribution of y values that we could get. We're going to be interested in the mean of those y values. For any value of x, there's a distribution of y's that has some mean. And that's where we get this second equation, which we will call the population linear regression equation. E of y equal beta 0 plus beta 1x. Again, you might recognize that just as the equation of a straight line, where the intercept term is beta 0 and the slope term is beta 1. Now what we want to do is we want to estimate the components of that line. We don't have all data in the population. That's the basic nature of statistics. But we do have a sample of data on the two variables. Now our estimated sample regression line is going to be denoted by the following notation. Y hat equals B0 plus B1x. B0 is going to be our estimate of the population intercept term. B1 is going to be our estimate of the population slope term. And Y hat is our estimate of E of y, the expected value of y given a value of x. The question is, how do we find the intercept and slope? How do we find B0 and B1? Again, we'll explain a little bit of the theory, but you don't have to worry about the mathematics. Let's go back to a graph here. Suppose this is a graph of my simple regression line through our sample data. Let's pick a particular point, let's say right here. Let's look at this vertical distance, which is our y distance. That's the y coordinate of that point. On the other hand, if I went up to the regression line, that is given a value of x, my regression line would predict a value on the line itself, which would be right there, and we call that y hat. Y hat represents the points on the sample regression line. Notice there's a distance between those 2 points. If this point is off the line, there is a distance y minus y hat, which is sometimes called the residual. In some sense, we want to fit a line through this data that in a sense makes those residuals small. We'd like a best fitting line that fits the data well. We'll notice that some of these residuals are positive, some are negative if they're below the line. So to get rid of the negative ones, we're going to square all of those residuals. And then mathematically, we're going to find the line that minimizes the sum of squared residuals. This is why this is called the least squares solution. Here's our residuals, yi minus y hat. We're going to square them, add them up, and we want to find a line that minimizes that quantity. Now, some of you in the class may have had calculus, and you learned how to find minimum and maximum points in calculus. Most of you haven't had that, so you don't have to worry about the mathematics. But you can use calculus to find the values of B0 and B1 that will minimize this quantity. And that'll give you your estimated linear regression line. So we need formulas for the slope and intercept. I'm going to give you 2 different formulas for the slope term. And again, you don't have to worry about where these formulas come from. They come out of calculus. One way to calculate B1, the slope term, is take summation xi minus x bar times yi minus y bar over summation x minus x bar squared. Personally, I don't like that formula that much because if x bar and y bar, if the means of your 2 variables are fractional, then you've got a lot of deviations here that are fractional in nature. And sometimes if you're doing the calculation by hand, that will get more difficult. By the way, we will also show you later how to do this on your calculator or how to do this on some computer programs. Obviously, the formulas in regression get fairly complex, and it's usually better to have technology help us with the calculations. But we are going to go through the calculations by hand also. If you took this top formula and played around with it mathematically, squared out the denominator term and so on, did multiplication in the numerator, you will get this alternative formula. B1 is equal to summation xi yi minus the sum of the x's times the sum of the y's over n, all divided by summation x squared minus the sum of the x's quantity squared over n. I recommend the second formula if you're doing it by hand. You'll need to just calculate a lot of sums. You'll need to sum the x's, you'll need to sum the y's. This is what we've called before the cross product term, multiply xi times yi and add it up. You'll need to square the x's and add them up, and this term is summation x quantity squared. Once you have the slope term, you can get the intercept term. The formula for B0 is just y bar, the mean of the y's, minus B1, your slope term, times x bar. Notice that you have to do the slope term first because you need the slope term to get the intercept term. In this formula, again, y bar and x bar are just your sample means of your two variables. So to do a simple regression, you have your model. You're going to go out and take a sample on the two variables, and you will perform the calculations that we just showed you. Let's do an illustration. A researcher was interested in the relationship between a student's grade on the final exam and the hours he or she spent studying in the 3 days prior to the final exam. A sample of 6 students from last semester gave the following data. So suppose we have the following. We were able to survey students and get how much time they studied in the 3 hours prior to the final, or 3 days rather prior to the final. And this was their grade on the final exam. First again, we always have to determine which variable is x and which is y. Well, it probably seems kind of logical to argue that your grade is a function of study time. So grades would become the dependent or y variable. Study time becomes the independent or x variable. So we're going to calculate the regression equation, and then we're going to use it, we'll show you, to predict the grade for a student who studied 9 hours and interpret the value of the slope coefficient. I've left some extra columns here because these are some of the other calculations that you're going to have to do. You're going to have to multiply x times y. You're going to have to get x squared and y squared. So here's all of the intermediate calculations that we need. Again, grades is our y variable, study hours is our x variable. We need to sum the y's, which adds up to 450. We need to sum the x's, which adds up to 42. Down here, I've also calculated the means of the two variables. Y bar would be 450 divided by 6. We have 6 observations, which would be 75. And x bar would be 42 over 6 or 7. xy, we simply multiply across in these columns. 90 times 10 is 900. 70 times 5 is 350, and so forth. Those add up to 3,400. Square all of the x's and add them up, so take 10 squared to get 100, and 5 squared to get 25, and so on. Those add up to 346. And the last column, y squared, 90 squared is 8,100, and so forth. And those add up to 35,350. Again, you can see that there's quite a bit of calculation to do by hand to do a regression, even here with only 6 observations. Then go through the formula and do the calculation. I've just plugged the numbers into our formula. Summation xy minus the sum of the x's times the sum of the y's over n. Summation x squared minus the quantity summation x squared divided by n. If you work this all out, you should get a slope term of 4.807. And again, later on, in future parts of this module, we'll show you how to get the same result on your calculator or on a computer program. Once you have the slope, you can get the intercept, which turns out to be 41.34. That gives you the following estimated regression equation. Y hat is 41.34 plus 4.807x. Now let's interpret that regression equation. Remember how to interpret the slope of a line. The slope of a line basically says for every 1 unit change in x, what do we predict on average that y will change by? So the 4.0807 is basically saying every hour, every additional hour of study time adds about 4.807 points to our average grade. And we've got that here on the next slide. For every additional hour of study, we estimate the average grade on the final increases by 4.807 points. We could also interpret the intercept term, but you have to be careful with that. Remember, technically an intercept says that if x was 0, let's go back to our previous slide, if x was 0, we would predict the grade to be 41.34. One problem sometimes with predicting the intercept term is it might be outside the range of your observed data. If we go back to our numbers for just a moment, we didn't have any x values close to 0. So when we set x equal to 0, we're actually, in a sense, extrapolating. We're going outside the realm of the data that we've observed. We don't really know if this relationship holds outside that range. So you should always be a little bit careful in interpreting, especially the intercept term, because it might not have that much validity. And that's the end of part 1. And coming up, we will take a look at how well does our regression equation seem to fit the data, and can we do hypothesis testing on our regression.